We have a configuration here of two resistors and two capacitors, and we're asked to find delta V across A and B when the switch is open and when the switch is closed. And just for fun, let's go ahead and find the charge on those capacitors in both cases. Okay, so when the switch is open, there's no current flowing through those capacitors. So we could redraw the circuit if we'd like, and it would look something like this. This symbol indicates that the voltage is 0 at that location. That's our ground. And the voltage is given as 18 at the top. And if there's no current flowing, then there's no voltage drop through a resistor. So we can sort of take them out of the circuit in this case. So you can see here that this part of the circuit, I'll use a dashed line, is all an equipotential surface at 18 volts. And this part of the circuit, I'll use a solid line, is all an equipotential surface at 0 volts. So location A is over here at 18 volts. Location B is over here at 0 volts. So A is 18 volts higher potential than B. Now I also want to find the charge on each of these capacitors. That's pretty straightforward in this case. We know that the charge on the 6 microfarad capacitor, that's this one, the charge on the 6 microfarad capacitor is its capacitance times its voltage, and the charge on the 3 microfarad is its capacitance times its voltage, and they are both in parallel, both have 18 volts across them. So this is 6 microfarads times 18 volts, 108 microcoulombs. Three microfarads times 18 volts, 54 microcoulombs. It should be half as much because they both have the same voltage and the capacitance is half as much. That looks good. And I think we're done with part A. So for part B, we'll close that switch. And what do you think the voltage is going to be between A and B in this circuit when that switch is closed? Basically, the circuit's going to look something like this. Here's A, here's B. So the voltage at A better equal the voltage at B because they are shorted out by that switch. That switch is a conductor, perfect conductor, and it's shorting out A and B. So VA and VB are the same now. Delta V AB is 0. VA equals VB. Let's go ahead and find the charge on both of those capacitors. And what I'm going to do is I'm going to redraw my circuit over here. Those capacitors are not going to allow current to flow through them. A capacitor is an open circuit. Current cannot pass through it. So as far as the current is concerned, the circuit looks something like this. This is a 3 ohm and a 6 ohm. So since V is equal to IR, the current through this circuit, once it's hit some steady state condition and the capacitors have reached a steady charge, is the voltage across them over the resistance. That's 18 volts over 9 ohms is 2 amps. So I have a 2 amp current flowing through my circuit. And so I know that this whole section up here is 18 volts, and this whole section down here is 0 volts. And the question is, what is this section in the middle? And if I have a 2 amp current, then I come from 18 through this resistor. I have to have a voltage drop through this resistor of I times R. I is 2 amps, R is 6 ohms, so I have to drop by 12 volts. So that means this has to be 6 volts in the center section. And then I drop by 2 amps times 3 ohms, and that gets me from 6 volts to 0 volts. I drop by 6 more volts, so that makes sense. So this middle section here is 6 volts. So let's go back to our first picture. This is 18 volts. This is 6 volts, and this is 0 volts. So I have a delta V here of 6 volts, and I have a delta V on this upper one of 12 volts. So I have Q equals CV. So Q on my 6 microfarad capacitor is going to be C6 V6 microfarad. And so I've got a 6 microfarad capacitance, and I have 12 volts, gives me 72 microcoulombs. And on the 3 microfarad capacitor, that's this lower one, I have 3 microfarads, and it has a 6 volt drop, 18 microcoulombs. So the trick to this problem was actually for finding the voltages wasn't too bad, but going from our original circuit with the switch open, we could take out those resistors because they had no voltage drop across them because of the capacitors were not allowing current to flow through them. And with the switch closed, we did get current flowing through the circuit, through the 2 resistors to ground, and we could find the potential difference across each resistor, and each one of those resistors is in parallel with the capacitor, so we knew the voltage drop across the capacitors.